Hi, I'm Adrian Cockcroft. Today I'm going to talk to you about architecture trends and topics that I think are going to be interesting in 2021. I'm going to start with serverless, then talk about chaos engineering, failing over without. A little bit on Wardley mapping for technology evolution, hardware trends, and end up on sustainability. So I'm going to start with serverless first. And where did this all come from? I think this is just the latest outgrowth of microservices. If we look at it goes back quite a long time, and it's something I've been talking about for quite a while. Back in 2013 was when I adopted the term microservices, and this was originally my definition from a talk I gave around that time. So the point here is that you want loosely coupled service-oriented architecture with bounded context. You want to be able to change things independently and not know too much about the entire system in order to be productive. And we chose microservices to get speed and agility. So let's look at the current situation. How much speed and agility can you get if you're trying to build a new application from scratch? So one of the things that we do at reInvent most years when we have it in person is we hold a nonprofit hackathon for social good. That turn up. We have a nonprofit organization with a problem, and Monday at 8 a.m. the teams find out what problems there are, pick something, and have 12 hours to go build. Now, where would you start if you only had 12 hours with a small team? Well, it turns out in 2016, I was a judge at the hackathon and really had what I thought was a light bulb moment. Every team used Lambda, and in this half day, even though many of them, it was the first time they were using Lambda, they built extremely functional and scalable prototypes. Everybody, all the judges, all the attendees were just amazed at what they could build. So I went around and I started telling this story to other people and started hearing anecdotes back saying, yeah, you can build ridiculously complex, scalable systems in just a few days. So why doesn't everyone do serverless first? And there's a few concerns that you hear over and over again. So I went through this and I did a talk about this last May as part of the serverless first function. And you can go find that talk to get a deep dive. But I went through all of these different reasons that I hear and went through all the different ways that we have answers for these objections or concerns. Now, what you've seen in reInvent in the last few weeks, the announcements, we've seen portability, better portability with container support. We've seen more scalability with 10 gigabytes and 6 virtual CPUs for a single function. And we've seen the ability to build more complex configurations using Proton. There's a couple of other updates that have happened since I first gave my talk. One of the limitations with Lambda originally was that there was a limit of 512 megabytes that could be bundled with the function. Now, if you're building deep learning models, sometimes they end up much bigger than that, and you want to deploy that model as a function, and it was difficult to figure out how to do that. So what you can do now is use Amazon EFS to NFS mount a file system that contains those models. That gives you, terabytes per file and up to 25,000 concurrent connections. So this gives you a very powerful way to share extremely large data files, which will be mounted during the initialization phase of a Lambda function, and then all the executions of that function, that data will just be there. One of the other things, as I mentioned, was the support for common build pipelines. So you can now deliver both serverless and container workloads using the same production pipeline. You can deliver them both wrapped in containers. And this really helps you build a single path for getting code into production, but it also makes it easier to transition from, say, your first prototypes built with serverless that are used for maybe low traffic rate workloads. As one of those workloads goes to an extremely intense, highly scaled workload, it may make sense to have an auto-scaled, Fargate-based, container-based service, and it makes that transition easier. So the bottom line is that serverless is the fastest way to build a modern application. And if you object, you have one of these objections, let us know what to work on next, because we're always looking for the next few things to work on. Another thing that Andy Jassy said during reInvent was that the half of all the new services built at AWS are being built on top of AWS Lambda. So this isn't just a fringe thing now, it's becoming very much a mainstream thing. So go find all the other talks and sessions on this as well. Next, I'm going to talk about another topic that I've been talking about quite a bit in the last year, which is chaos engineering and failing over without falling over. So this is my sort of concise definition for chaos engineering. You want to experiment, you're running experiments to ensure that the impact of failures is being mitigated, because failures are going to happen, but you want to mitigate the impact. You have all these plans to mitigate those impacts, but unless you actually experiment to make sure that those mitigation plans are actually working, then you're not going to be successful. And one of the things here is that this is really becoming a little bit more of a common thing. But 10 years ago, we had the very first blog posts around Chaos Monkey. And what we've seen since is really a lot of people talking about it and just a few people implementing it as a kind of a daily thing that they do. And if we look at resilience in general, in the past we've had disaster recovery services as a pattern. And then we've now got this idea of chaos engineering, which has been adopted by a few people. But what we really want is continuous resilience. We want to be able to ensure that we know that the things we're building are being continuously tested and that chaos engineering isn't just a one-off thing that you do at some point. Now, if you think about this, we're building redundancy into systems so that if something fails, you can fail over to an alternative. However, the ability to fail over is complex and hard to test, so often the whole system falls over. So how can we do better at this? So one way of thinking about this is, rather than links in a chain, think of a rope which has lots of strands and gradually frays. Then eventually that last few strands will break. And that last strand is not the cause of the failure. Cause of the failure is you weren't tracking the system and trying to understand how frayed it was. So you've got to think about how much margin do you have left in your architecture. And the architecture has 4 layers to it. At the bottom, there's the infrastructure. You have to have redundancy there. Then you have to have a way to switch between alternatives. You have to have an application that knows how to not just keel over when something strange starts happening, and you need people that are well trained in doing the right thing when something goes wrong. And really there are 2 separate teams that have approximately the same concerns. The chaos engineering team is trying to probe the system to ensure that effective failures is being mitigated. But the security red team is also looking at that from the point of view of cyber attacks to make sure that the system is secure. One of the new services that was announced at reInvent is the fault injection simulator. This lets you run experiments to ensure that both availability and the performance impact of failures is being mitigated. And it's something that we had to build. In order to really do this properly, we had to get under the hood, we had to get behind the APIs and manipulate some of the underlying capabilities within AWS, things that aren't exposed via APIs. So you can't build a really detailed and powerful fault injection simulator to do chaos engineering the way we thought we needed to, if you just do it on the public APIs. So this is a quote that I've been using a lot. You can't legislate against failure, focus on fast detection response, meaning that you can't predict what will always go wrong. But if you can always detect it quickly and respond quickly, you can handle pretty much anything that gets thrown at you. There's been a lot of talk recently about observability. That's the fast detection piece. I want to focus a bit more on the response, which is the control piece. And let's see what we can learn from experts who've been working on controlling safety-critical systems for decades. It's a really interesting book here, Engineering a Safer World by Professor Nancy Leveson of MIT. This is a team that's been working on aeronautic safety in particular, things like air traffic control systems and the in-flight refueling systems. How do you build software that does those, that manages those things in a safe way? This book talks about having a control diagram. So this is a control diagram that I've adapted from the book to show you something that is broadly comparable to the way that we build web services nowadays. At the bottom, there's a data plane that contains the business logic. Customer requests come in, a web service does something, completed actions go out, disturbances happen. Those disturbances are adjusted by the control plane, maybe scaling up and down or replacing nodes or doing fraud filtering, all those kinds of things. All the code that isn't part of your business logic but is there to manage the system belongs in the control plane. There's a control algorithm, there's a model of the control process, and there's sensors and actuators. Above that, we draw the human controller. And controls always start at the top and go down, and sensors are the arrows that start at the bottom and go up. And that's kind of the standard way of drawing these. The human controller is watching over everything. They're using written procedures, environmental inputs. They're trying to make sure they know what's going on here. So what happens if there's a really big disturbance, something that the control plane can't cope with? So this is really about large-scale failures, and this is where you start thinking about failover because the automation's failed or the application's crashed, and that triggers a failover to an alternative system. So let's sort of simplify that diagram and show the human controller as the control plane and the routing service. But in this case, I'm going to show the routing service as a separate service and have it routing between 3 copies of the application running in 3 different availability zones. And we're going to make these assertions that we have the same data and services in all 3 zones. The failure modes are independent, and the application should work normally with a zone offline, and that routing service is in charge of switching and controlling that failover. So this is what we'd like to see. A zone goes offline, the control plane detects it, the routing service is controlled to no longer send traffic to that zone. There's a few retries, everything continues. That's what we'd like. But what could go wrong with this? The STPA model that's described in the book I referred to goes through all the different hazards. So if we look at this, this is the center metric checklist of the hazards that you would get in the upwards flow in this diagram. Missing updates, corrupted data, things coming in too quickly, things coming in too slowly, coordination problems. Degradation over time happens with software releases that gradually break sensors, and you don't notice necessarily until it's too late. But what's really likely to happen in practice is the control plane isn't clearly going to inform the humans that everything's taken care of, because that offline zone is going to delay and break other metrics and create a flood of errors. So it's one of those situations where all your dashboards light up red and you're still trying to figure out exactly what is going on underneath. If we look at the model, this is what's in the human's brain and in the control plane's model, the automation that takes a sensor and turns it into a control. That's the model. What could go wrong? Well, you can have mismatches, coordination problems. Maybe there's multiple human controllers, each have a different idea about, well, this sensor, this combination of sensors means we should do these things. So the models aren't all in sync. And again, there's other things that can go wrong in that list. So what's likely to happen in practice is the human controllers are going to disagree about what they need to do. Floods of errors, displays will be lagging reality by several minutes, and their runbooks will be out of date. So they will be just confused. And then if we look at the controls themselves, what could go wrong with that? Again, this is the standard STPA checklist for hazards. But maybe the control hasn't been provided, you did it too early or too late, you do things in the wrong order. Again, coordination problems and degradation over time. I'm sure we've all seen runbooks that are out of date, that kind of thing. So again, what's going to actually happen? In this particular case, the humans should not need to do anything, but probably they'll be confused, they'll try to fix things, they may break things. Some of the tools don't work or are misconfigured, or you think it's going to do one thing, it does something else. So unfortunately, what typically happens in this case is the inrush of extra traffic and all the extra request traffic coming in, all the retry traffic is going to basically take out the whole system. The operators will probably make it worse. And you're likely to end up completely fallen over. So how can we do better? There's a few things. One is alert correlation. There are floods of alerts. I mean, you have a normal level of alerts that your system's built to cope with, but in these kinds of failure modes, there's going to be orders of magnitude more alerts. So how do you take those? How do you cope with those floods of alerts? And how do you turn them into actionable insights? There's a number of vendors in this place, and there's also a new service that we recently announced called Amazon DevOps Guru, which looks at your system, looks at your logs, tries to recommend what's going on and what you should do about it. And then the other thing is to run really regular chaos engineering experiments to try this out and be sure that you know what's going to happen. Exercise the people and the systems. And the fault injection simulator is going to help with that. Now, these retry storms, one of the reasons that they're a problem is that you've got a lot of work amplification when you're retrying stuff too many times. So you should really look through your system, reduce retries to 0 as the default, and then just turn on retries at subsystem entry and exit points. And reduce timeouts, because if you're retrying something and then at the edge, the original request is given up waiting. Right, so that request is now orphaned. The original request is given up waiting, so you're just wasting time repeating work that's not going to have any productive use. The other thing is to route calls within the same zone. If you manage to, if work is happening within one availability zone, you really only want to call services that are in that actual zone, unless you're replicating data across zones. That will help reduce the number of retries. Now, the thing that makes this easier in the cloud is that we have symmetries. We have a high level of automation, consistent configuration as code, consistent instance type, services, version zones, and regions. And there's some good principles here too. If you can make it the same, make it look and act identically. And if it's different, make that clearly visible and keep testing those assumptions. Now, if we look at multi-region, I don't really have time to go into this, but the most important thing is to get zone failover completely solid before attempting multi-region, because you need to be able to tell which of these things is happening, and that's not at all obvious in most cases. Use STPA in a similar way to look at multi-region hazards, and follow the well-architected guide patterns. So I think what we'll be seeing is as data centers migrate to the cloud, those fragile manual disaster recovery processes are going to get standardized and automated, and we'll move failure mitigation from this scary testing experience that people tend to do once a year or not at all, to something that's automated and continuous. Now I'm going to talk about Wardley Maps. Most of you probably haven't heard of Wardley Maps. It's something that I'm finding early adopters using. So looking at it on the trends, it's just started to bubble up. I think in another few years, this is going to be much more widely known. So what is a map? Well, a map always allows you to define position and movement. And a Wardley map is about strategic context, barriers, and actions. What are you doing? What is the position and movement of your business? And there's some good examples here. The kind of things we use it for, the evolution of technology from a custom built to utility. Technology stack migrations from data center to cloud is where I see the easiest place to start using it. But it's also good for doing make versus buy decisions, and there's some good examples in open source product strategy. So I'm going to take some examples from Kubernetes. There are really too many Kubernetes projects. I can't remember half their names. They're all in different stages of evolution. So that seems like a good thing to put on a map. So the CNCF built a map. Well, they built a landscape, but it's not really a map. It's an eye chart. There isn't really position and movement here. It's just a collection. So if we plot this on a Wardley map, here are some of those projects, but arranged in a way that makes more sense. So at the top of your value chain, you have the user and the operator. And those are developing or using these tools, and those tools depend on additional things. So the projects form a hierarchy where one project requires another project, working all the way down till you get to the bottom, where you have basically data centers and things like that. In this case, we can see that over on the left, I've got code that's written by the user, your own code. That will be running as an application pod. So that is a novel new thing that didn't exist before. That's using other capabilities like, say, Kubeflow and the AWS plugins, which are not CNCF projects, but which they're commonly used by people in their configurations. Then we look at the next block over is things which are CNCF projects, which have been adopted, and they have some notion of stability. They've been through the technical steering committee review. And on the right, you've got those projects bundled into services like EKS, and also dependencies upon AWS capabilities like EBS and S3, things like that. So that's more of a landscape. If we look at what's been happening in this, we've got new Grafana and Prometheus services. So we take some of the observability pieces where you would go and install these projects yourself, and we've made them into AWS services along with the OpenTelemetry distribution. So that gives you the ability to sort of map, so which services should you move, what should you expect to be moving into a CNCF project? What are you expecting to move to become available just as a service? You can kind of think about this left to right evolution. So some of the results from mapping. You get successful products and services due to better situational awareness, strategic decision making, shared understanding of moves. You can look at a map and everyone can look at it and get some understanding about what's going on that map. And then also there's a lot of discussion in Wardley mapping around application of doctrines. I don't have time to get into that, but there's a lot more to Wardley mapping than just these simple diagrams. A lot of good detail there. So I'm going to talk briefly about hardware trends. What is big data? Big data is data that's too big to process on one machine. That's why we started building Hadoop clusters a few years ago. But the machines keep getting bigger. Here's the sort of biggest sort of machine I've heard of recently. This image is taken from a Jeff Barr blog post talking about the EC2 Ultra clusters. 4,000 or more A100 GPUs on 400 gigabit links into a petabit scale fabric. This is a monstrously powerful machine. What could you run in that? It's quite an interesting capability. So if we look at this as, on the left side, I've got sort of the bandwidth of memory, and on the bottom, I've got capacity. And they're not linear, just to sort of try and get this to fit on one graph. If we start at the top right, if you can fit your entire problem into 40 gigabytes of memory, you can run inside a single NVIDIA A100 GPU. That gives you over 1 terabyte per second of memory bandwidth. It's incredibly powerful, and thousands of processors to work on that memory. Now, as your program gets bigger, you may need to run it on P4D across all 8 GPUs. So what that gives you is 600 gigabytes per second of GPU memory bandwidth on the NVLink that connects them together within a single instance. Again, a lot of bandwidth and a lot of compute power. Then if you just look at the CPU component of that P4D, the main processor, that's 2 Intel Cascade Lake processors. You've got 1.1 terabytes of memory, and you've got about 30 to 40 gigabytes per second of main memory bandwidth. It's around that range. So the next point over is the 24 terabyte memory, 8 Cascade Lake processors. It's possibly slightly slower because the large memory systems tend to have, it just takes a little bit longer to get across all that memory. But an enormous amount of memory if you can fill that up and put all of your application in it. And then that Ultra cluster, which is 4.4 petabytes of memory, which is obviously a huge system with a huge amount of bandwidth. The bandwidth in and out of the nodes is actually almost as much as the bandwidth within the nodes, which is an interesting point here. So how can we take advantage of more memory? We can do in-memory analytics. We can do very large graph databases. And then there's a few more novel ideas to use the memory and to connect a low latency network, use shared memory to avoid serialization overhead perhaps. But maybe you could put all the pods and instances on the same node and come up with a more efficient way to couple them together. And in that case, you'd have to do fast replication for persistence. Some interesting work to watch here. This is a few startups and research teams. You can run your CFD simulation inside the GPU. There's a couple of memory-based operating systems from Santa Cruz and from Verge. Brightlight's a database running completely inside the GPU with a Postgres compatible interface. It's quite interesting. And then Scream is a data warehouse with GPU acceleration. Okay, finally, I'm going to talk about sustainability. And I'm going to start with the climate pledge. In 2019, Amazon came out with a climate pledge. Jeff Bezos announced it. Basically, it's a pledge to reach the Paris Agreement 10 years early, but be net zero carbon by 2040. The pledge now has 31 signatories. Some of them were announced during this week. Got a few of them on this plot, and we've now got Unilever, Verizon, Siemens, Microsoft, and Best Buy included in this. So we've ordered over 100,000 fully electric delivery vehicles, investing 100 million in reforestation projects, and this climate pledge fund 2 billion to back visionary companies helping this transition to a low carbon economy. We've also announced very recently an extension of our renewable energy projects, 26 new projects totaling 3.4 gigawatts of power, bring our total investment to 35 projects just this year and more than 4 gigawatts of capacity. We announced some earlier in the year. This is the largest corporate investment in renewable energy in a single year, and these new projects will make Amazon the largest ever corporate purchaser of renewable energy. We've got a total now of 6.5 gigawatts of wind and solar projects. Not all of them are up and running right now, but over the coming year or two, we'll see this capacity coming in and powering not just AWS's data centers, but also the Amazon corporate offices, fulfillment centers, and the whole of Amazon. So this isn't an AWS level thing. It's something that's happening at the Amazon level. And in fact, what you're seeing is that we're really optimizing at the Amazon level rather than just optimizing for what AWS would be needed to do. However, if you do move to AWS, the energy efficiency is so much better for our data centers that on average, you typically see an 88% reduction in carbon footprint compared to running workloads on premises just from moving to AWS. And then we've also committed to power operations, 100% renewable energy by 2030. And we're currently on a path to reach that milestone 5 years early in 2025. We've also got the Sustainability Data Initiative. This reduces the technical barriers with getting large data sets. So this is part of our Open Data Initiative. And the way this works is it gives easy access to petabytes of foundational data. It's hosted free of charge in public Amazon S3 buckets, managed by the owners of the data themselves. So the owner of a data gets an AWS account, puts data in a bucket, and applies to this program. We then subsidize the cost of that bucket so it appears to everybody as a free resource to be used. And when you're massaging petabytes of data, it's really good to have the costs of storage and the networking costs completely covered. There's a Linux Foundation organization called OS Climate. This is to take things like ASDI, this is one of the reasons we're involved, and use that to build on top of it a data lake with analytics capability, which is we can use to model the impact of climate on the valuation of assets. So this is so that investors can look at what's going to happen to their portfolio of assets. It also is to provide companies with standard ways to report their climate footprint and their exposure to various climate risks. A few contributions here. We're founding members of the organization, the primary technical partner for initial development. We're providing professional services and credits, and we're extending ASDI. And myself and the SA for the account, Madhu Busa, are the joint technical lead role on this. So just to wrap up, sort of a call to action. There's a lot of programs here that you can use to architect solutions, achieve your own sustainability goals. Ask around in your own organization, do you understand what your organization is doing about climate, and how can you influence that? Look for opportunities to optimize your architecture and share the solutions you build. I'd like to see a lot more talks at reInvent in future about with the sustainability aspects. Now, here's some resources related to the talk, some about resiliency, a few blog posts, my failing over without falling over the serverless first talks, and a few other blog posts on various details. And my book list, because I like to recommend a lot of books in my presentations. And then generally the architecture track and the well-architected framework, there's a lot of information here that you can go dig up and find all of these things that we have, an awful lot of information in the architecture track at reInvent. And I think we're continually trying to extend the well-architected framework, particularly around resiliency, and that's a really key one for you to work on. So thank you. I hope you enjoyed that talk, and I'll see you around. Thank you.